Hello and welcome to the Unit 3, Section 3 video on simplifying irrational and imaginary solutions. So we're going to start off by talking a little bit about review here. So back in geometry and even back in Algebra 1, you learned a little bit about the properties of radicals. So let's start off by just talking about what the parts of a radical are, or what a radical statement are. Well, first of all, the radical itself is this symbol. Now, you often call it a square root symbol, but the square root only applies for certain situations. So this would be your radical. And that situation that it applies is related to this n value. This n value is called the index. And so when you have the index being 2, that's when we call this a square root. Now, you'll often say, well, I don't see a number 2 there when we have a square root. That's because when we don't write the number there, the index is understood to be 2. And then if you have some other number there, then we know it's going to be that particular index. And then finally, whatever's inside of the radical symbol, that is called the radicand. Okay, so as we just stated, a square root is a radical with an index of 2. And most often, you will not see that number 2 written in as the index. It will not be written, and it will just be understood that it is a square root. A square root is simplified if the radicand has no perfect square factor other than 1. A perfect square is a number that can be multiplied in on itself. Okay, it's any number that is squared. Okay, so let's take a look at a list of perfect squares. Many of these you are going to be familiar with because they're just part of your multiplications tables that you learned back in 2nd, 3rd, 4th grade, somewhere in that neighborhood back in elementary school. Okay, so 1 squared is 1, 2 squared is 4, 3 squared is 9. These numbers, 1, 4, 9, 16, 25, 36, 49, 64, these are perfect squares. And these are the numbers that are going to be important when we go to simplify square roots, because these are the numbers that need to be factored out of the radicand to simplify your square root. And I've listed all the way up to 20 squared, which is 400, just for your information. So let's take a look at some examples, and in these examples, we're not necessarily concerned with what the simplification is, at least yet. We are going to determine simply if this root is simplified, okay? If the square root is simplified. So let's start off with the square root of 3. Well, the square root of 3, the only perfect square that is less than that is 1, and we don't really count 1 because everything can be divided by 1. So since there are no other perfect squares less than 3, there's nothing that we can pull out of 3 to get the square root of, so therefore it is simplified. Square root of 6, well, the only perfect square that's less than 6 that we're really concerned with is 4, and we can't factor 4 out of 6 evenly, so therefore square root of 6 is simplified. Now, the square root of 8, if we look back again, we've got this 4. 4 can be factored out. So since 4 can be factored out of 8, this is not simplified. And the reason it's not simplified is because 4 is a factor of 8. For the square root of 10, well, we can't pull 9 out evenly, and we can't pull out 4 evenly, so therefore, square root of 10 is simplified. Square root of 12, well, 4 is a factor, so therefore it's not simplified. And it's not simplified because 4 is a factor of 12. And then for the square root of 18, well, 16 won't come out evenly, but 9 will. So therefore, square root of 18 is not simplified. And that is because 9 is a factor of 18. So now we've talked about whether it's simplified or not. We need to think about, if it's not simplified, how can we simplify it? And what does that look like? So that brings us to the product property of radicals. A radical expression is in simplest form if the radicand has no perfect square factors other than 1. Okay, because remember, we don't really count 1 squared, even though 1 is a perfect square. We don't count it because everything can be divided by 1. So the product property of radicals can be used to simplify radical expressions. And it simply states that for any numbers a and b, where a is greater than or equal to 0 and b is greater than or equal to 0, the square root of a times b equals the square root of a times the square root of b. In other words, we can split that square root apart between the things that are being multiplied underneath that square root symbol. Another thing I want to bring up here is it says a has to be greater than or equal to 0 and b has to be greater than or equal to 0. Why can we not have a negative number under the square root? I'll let you think about that for a second. So the reason we can't have a negative number under the square root is, what do we do to square a number? We multiply it by itself, right? If we had, say, negative 3 squared, that would be 9. If we had negative 2 squared, that would be 4. So every time we square a number, we get a positive number. So if we were undoing a square, it would make sense that we would never have a negative number to undo, because we can never get to a negative number by squaring something. So that's why we can't have a real solution. Now that's going to be the key. We cannot have a real solution when we take a square root of a negative number. Toward the end of this section, we're going to talk about what happens when you have a negative number under the square root. But for now, let's consider positive numbers. Consider the square root of 8 from the example 1. It was not simplified because 8 has a perfect square factor of 4. Using 4 times 2 equals 8, we can use the product property of radicals to simplify this down. So we can rewrite the square root of 8 as the square root of 4 times 2. Well, this is a product property, right? We've got two things being multiplied under the square root symbol in the radical. So we can split that up as the square root of 4 times the square root of 2. And the square root of 4 is simply 2. And it's multiplied by the square root of 2. So that would be the simplified form of square root of 8. It would be 2 times the square root of 2. So let's do a few of these for practice. Let's simplify each of these radicals. Square root of 12, we can break that down into the square root of 4 times 3, which gives us the square root of 4 times the square root of 3, which is 2 times the square root of 3. All right, for the square root of 18, we know 16 can't go into it, but we do know that 9 can go into it. In fact, we stated that in the first example. So we can break this down into the square root of 9 times 2, which is the square root of 9 times the square root of 2, which gives you 3 times the square root of 2. All right, 112, square root of 112. Here's where I'm going to tell you a little piece of information that will help you out in narrowing it down in terms of what perfect squares can go into it. You can start with the perfect square that is immediately less than half of that value. Okay, so you have 112. What is half of 112? Well, it's 56. So you don't have to look at 100 and 81 and 64. Those are already out because they're more than half of the value of 112. So you know none of those can be factors. So let's start with the first one that's less than that, 49. Well, 49 is not going to go into it. 36, 36 won't go in evenly. Neither will 25, but 16 will. And you can always use your calculator to test all of these perfect squares to see if they will multiply in. So we have 16 times 7, which breaks down into the square root of 16 times the square root of 7. Write that a little neater. Square root of 16 times the square root of 7, and that gives you 4 times the square root of 7. All right, for 150, the square root of 150, we are going to have this break down into what? Well, sometimes I like to think of it in terms of money. If this were $1.50, can we put so many quarters into $1.50? Yes, we can. We can put 25 cents into $1.50 6 times. So let's try 25, because 25 is a perfect square, times 6. Well, you got the square root of 25 times the square root of 6, and that gives you 5 times the square root of 6. Square root of 72. Now, here's where you can actually do this in more than one step. The largest perfect square that will go into it is 36, and that will go in twice, because 72 divided by 2 is 36. But what if you don't recognize that? What if you say, well, I know it's 8 times 9, and 9 is a perfect square. Well, let's start there. Let's say that you break it down into 9 times 8, because you recognize 9 as a perfect square. Well, look at 8 again. Can we factor another perfect square out of 8? Yes, we can. We can factor out a 4 times 2. Okay? And what that gives us is the square root of 9 times the square root of 4 times the square root of 2, which gives us 3 times 2 times the square root of 2, and 3 times 2 is 6. So you still end up in the same place. Even if you didn't recognize 36 and 2 were your most direct way to factor it, you can still get there by doing it in multiple steps. All right, for a square root of 98, the largest perfect square that will go into that is 49, because it's 49 times 2. So that gives us the square root of 49 times the square root of 2, which gives us 7 times the square root of 2. Let's do 3 more of these. So for the square root of 48, we can break that down into 16 times 3. So we get the square root of 16 times the square root of 3, which equals 4 times the square root of 3. 162, we can break up into 81 times 2, which gives us the square root of 81. Let me see if I can clean that up a little bit for you. Square root of 81 times the square root of 2, which is 9 times the square root of 2. And then finally we have the square root of 200. We can break 200 up into 100 times 2. Square root of 100 times the square root of 2. That gives us 10 times the square root of 2. So we're starting to get pretty good at simplifying radicals. Well, this is going to become helpful when we get into our next couple of properties here. So now let's talk about the quotient property of radicals. You can divide radicals and simplify radical expressions that involve division by using the quotient property of radicals. And it simply states that if you have any numbers a and b, where a is greater than or equal to 0 and b is greater than 0, that the square root of a over b is equal to the square root of a over the square root of b. So in other words, if you have a fraction under the square root, you can split up the fraction you can split up the square root for each part of that fraction. And now note here, we cannot have b equal to 0 because we cannot divide by 0. So therefore b is only greater than 0 since this is the denominator. And it can't be negative because it's under a square root. So for example, the square root of 4/9 can be rewritten as the square root of 4 over the square root of 9. We know what those are. Those are both perfect squares, so we can simplify it down to 2/3. So let's do a few of these. For this one, we have square root of 16 over 25. That's the square root of 16 over the square root of 25, which gives us 4/5. For b, we have the square root of 49 over the square root of 4. Well, that gives us 7/2. For c, we have the square root of 121 divided by the square root of 36, which that becomes 11/6. Then we get over here to the square root of 1 over the square root of 9. That gives us 1/3. For e, we have the square root of 4 over the square root of 64. And that gives us 2/8, but we're not done yet because that can be reduced down to 1/4. And then finally, we have the square root of 100 over the square root of 25. That's going to give us 10 over 5, which is simply 2. So you'll notice that these problems were fairly quick to do. But what if what's on the top and bottom don't become nice perfect squares that we can just take the square root of? Then what? Well, that brings us to our next part. That brings us to rationalization. In rationalization, expressions in simplest form cannot have square roots in the denominator. We must rationalize any denominator that contains a radical. For denominators with a single radical, we multiply both the numerator and denominator by a radicand that creates a perfect square. So here is, in example form, what we're talking about. So we can split up a into the square root of 5 over the square root of 2. But we can't have a radical in the denominator. And we can't simplify either of these either. So what we're going to do is we're going to multiply the top and the bottom by our radical that's in the bottom. And when we do that, we end up with the square root of 5 times the square root of 2 over the square root of 2 times the square root of 2. Well, the top ends up being the square root of 5 times 2. The bottom ends up being the square root of 2 times 2. And so in the top we get the square root of 10. In the bottom we get the square root of 4. And so we end up with the square root of 10 over 2. Now you'll notice that when we multiply a square root by itself, here's another way to look at it. We had square root of 2 times the square root of 2. Square root of 2 times the square root of 2 is just the square root of 2 squared. So the square root and square cancel and you're just left with what's under the square root symbol. And that's what's often going to happen when you rationalize the denominator. So let's look at b. We've got the square root of 6 over the square root of 5. Those are already both in simplest form. So we're going to multiply by the square root of 5 over the square root of 5. And we end up with the square root of 30 in the top, because 6 times 5 is 30. In the bottom, we end up with 5. For c, we have the square root of 7 over the square root of 3. We're going to multiply the top and bottom by the square root of 3. And that is going to give us square root of 21 over 3. Moving on down to these last few examples. We have the square root of 1 over the square root of 6. We're going to multiply the top and the bottom by the square root of 6. And in the top, we're just going to end up with the square root of 6, and the bottom will end up with 6. So square root of 6 over 6. In E, we've got a couple of things we can do. We have the square root of 9 over the square root of 8. But you'll probably recognize square root of 9, well, that's just 3. So we can go ahead and take the square root of that and work from there. We still have the square root of 8 in the bottom. And even though we can simplify it, let's go ahead and multiply the top and the bottom by the square root of 8. That gives us 3 times the square root of 8 on the top and 8 on the bottom. But we can simplify that square root of 8, right? So let's do it now. We've got 3 times 4 times 2, square root of 4 times 2, over 8. So we end up with the 2 coming out, 3 times 2 times the square root of 2, over 8, which would be 6 over 8, which would reduce to 3 over 4. Because that 2 and that 8 can reduce down to 1/4. So you get 3 square root of 2 over 4. In F, we have the square root of 17 over the square root of 12. If we multiply the top and the bottom by the square root of 12, we're going to end up with 12 in the bottom, but I'm going to keep the top as 17 times 12 underneath that radical sign, because it's easier to simplify this 12 than to put it together and try to figure out what our perfect squares are. So when we do that, we can simplify that 12 into 4 times 3. Can't do anything else with the 3, can't do anything else with the 17, but we can pull that 4 out. So that 4 pulls out and becomes 2. 17 times 3 is 51, and you have 12 in the bottom, and then this reduces down to the square root of 51 over 6. For G, we have the square root of 4 over the square root of 18. If you want, you can go ahead and simplify that denominator. We can also simplify the top. Square root of 4 is just 2. And if we simplify the denominator and we pull that 9 out, we have 9 times 2, which gives us 3 times the square root of 2. Well, now we can simplify or rationalize just doing square root of 2 over 2, which gives us 2 times the square root of 2 on the top and 3 times 2 on the bottom. And so we end up with 2 times the square root of 2 over 6, which is square root of 2 over 3. For H, we have square root of 12 over the square root of 32. And honestly, before we even do that, can we reduce this fraction before we even do anything? Well, we know that 4 will go into both of these. So we can simplify this fraction as 3 over 4 will go into 32. How many times? 8 times. So we have square root of 3 over the square root of 8. We know 8's not simplified, but that's okay. We'll go ahead and rationalize with it as it is. So that gives us square root of 3 times 8 over 8. Well, we can pull out a 4 from that 8. So we end up with 3 times 4 times 2 over 8. And so we end up with 2 times the square root of 6 over 8, which reduces down to the square root of 6 over 4. All right, and then the final example. This is the square root of 32 over 3, square root of 3. We rationalize by doing square root of 3 over the square root of 3. We get the square root of 32 times 3 over 3. Well, we know we can pull a 4 out of 32. So that's going to be 4 times 8, 4 times 8 times 3 over 3. But then we look at the 8 and we notice that we can pull out another thing. We can pull out another 4. So we have 4 times 2 times 3 over 3. And then we end up with 4 coming out. 2 times 3 is 6. And you have 3 in the bottom. So 4 times the square root of 6 over 3. Okay, so moving on to this final page. At this top of this final page, I've given you some things to think about when you're simplifying. Okay, when simplifying radical expressions, you need to check the following conditions to determine if you have the expression in simplest form. First, you can have no radicands with perfect square factors. So all the perfect square factors have to be factored out of that radicand. The radicand can also contain no fractions. So you'll have to use the quotient property to split up your square roots. And then from there, you'll likely have to rationalize because we cannot have any radicals appearing in the denominator. So if you've achieved all these three things, then you are good to go and you have simplified your expression. And of course, one other thing that you'll want to think of is whatever comes outside of the radical, to make sure it's reduced down to its simplest form as well. All right, this brings us down to our final short section here in this section of notes. And that is imaginary solutions. So what happens if you do end up with a negative number in the square root? Can we even do that? Well, at some point, someone realized that maybe we can evaluate negative square roots if we use what's called imaginary numbers. And all this means is we are going to define that the square root of -1 is a letter as a variable, and that variable is I. Okay, so we're just going to say I is equal to the square root of -1. Well, if we know what I is, can we find what I squared is? Well, I squared is simply I times I. And if we know that I is the square root of -1, we end up with the square root of -1 times the square root of -1. Well, that's just the square root of -1 squared. And when you square the square root, you end up with -1. So if you square an imaginary solution, then you're going to end up back with a real solution. And that real solution is -1. Now, I don't want to go too deep into imaginary numbers because really we're just using it as a tool, and that tool is that I is going to be the square root of -1. That's really going to be the only tool that we're going to use here. But I do want to expand just a little bit. If we simplify the successive powers of I, do you see a pattern? So we know that I to the first is I. We know I squared is -1. We just showed that. Well, I to the third, we can split up into two things that we just found. Using our exponent rules, I squared times I is I to the third. We know I squared is -1, so we put that here. I, we know, is just simply I. -1 times I gives us -I. So I to the third is -I. Well, now if we come down and take our fourth power of I, we can split that into I squared times I squared, which is -1 times -1, which gives us +1. Well, then when we go to powers above that, we can simply break down I to the fifth, I to the sixth, I to the seventh, and I to the eighth down into the I to the fourth times something from this first column, which means that we end up repeating the same sequence, I, -1, -I, 1. And that continues on every 4. You're going to cycle through that for successive powers of I. Okay, so that's just something I wanted to bring up, something that we're always looking for patterns in math, and there's another one for you. But the main thing we want to utilize here is that I is defined as the square root of -1. And we're going to use that to simplify these last 9 examples. So we have the square root of -64. we can split that up into the square root of 64 times the square root of negative 1. Well, we know what the square root of 64 is. It's 8. And we defined I as being the square root of negative 1, so our solution is simply going to be 8I. For the square root of 63, negative 63, well, we can split 63 up into 9 times 7, and then we have the square root of negative 1 out here. And so that's going to give us, square root of 9 gives us 3, square root of negative 1 gives us I, and then the square root of positive 7 is what's left over. So if you're given a simplification where you're going to end up with some number outside of the square root, an I, and a square root, that is the order that you would write them in. 3I square root of 7 would be the proper order to write it in. All right, square root of negative 108, we can split 108 up into 36 and 3. And we can, let me write that a little neater for you, 36 and 3. And we can pull out the square root of negative 1. And the square root of 36 is 6. Our square root of negative 1 gives us I, and then you have the square root of 3 left over. Can you tell me what the solution to the square root of negative 16 is without even doing any work? It's just simply 4I, right? Square root of 16 is 4. Got the negative, so that gives you the I. But here's the work just so you can see that that's true. You have the square root of 16 times the square root of negative 1. So it is just 4I. All right, 5 times the square root of negative 100. So this is going to give you 5 times the square root of 100 times the square root of negative 1. Square root of 100 is 10, times 5 is 50, and then you have I for the square root of negative 1. Square root of negative 32, we can split up 32 as 16 and 2. We have our square root of the negative 1 on the outside. Square root of 16 is 4. You have an I, and then you have a square root of 2. Negative square root of negative 45. Well, that negative is just going to be on the outside. We can split 45 up into 9 and 5. We've got our negative 1 being broken out as well. And that gives us negative 3I square root of 5. For this one, we have 1/2 times the square root of 48, which is 16 times 3, times our negative 1, square root of negative 1. 1/2 times the square root of 16, which is 4. 4 over 2 is 2. Then you have I, and then you have the square root of 3. And then finally, for the last one, we have negative 3 times the square root of 24, which can be broken down into 4 times 6. And we've got our square root of negative 1 on the outside here. Square root of 4 is 2, times 3 is 6, so you got negative 6. You've got your I, and you have the square root of 6. So really, the only extra step here is we pull out our square root of negative 1, and we make that I, and we stick it in as part of our solution. All right, this concludes this section. We will be getting back into talking about quadratics more in the next section.